Hello and welcome to the channel Science, Maths and Engineering. Today we are going to solve the GATE 2011 Mechanical Engineering paper part 2. So let's get started. These are 2-mark questions and in this part we will cover 15 questions. So question number 26. A torque T is applied at the free end of a stepped rod of circular cross sections as shown in the figure. The shear modulus of the material of the rod is G. The expression for D to produce an angular twist theta at the free end is okay. So in this problem, we are given a torque T that is applied at the free end. Then it is a stepped rod. Here cross section is twice D is the diameter. Here D is the diameter. This length is L and this length is L by 2. Now as we are putting a torque here, so this part of the shaft will get a twist. Along with that, this part of the shaft will also get a twist. So we will have to add the or both the twist angles. So then after that we can get the expression for D. So the solution is D is equal to 18 TL divided by pi theta Z to the power 1 by 4. So let us check the solution. The polar moment of inertia for a circular cross section is J is equal to pi d to the power 4 divided by 32. Okay. The moment of inertia along x-axis or y is pi d to the power 4 by 64. So the polar moment of inertia, that is IZZ, is equal to what? Pi d to the power 4 by 32. Then angular twist theta, we know it is equal to TL divided by GJ, where J is already, we know, the polar moment of inertia, and Z is the shear modulus of the material. Okay. Now we know D1 is equal to twice D, D2 is equal to D, as in the figure it is given. L1 is capital L and L2 is L by 2. So theta 1 would be TL divided by G pi by 32, that is the value for J, into 2D to the 4. So this expression comes. Similarly, theta 2 is this 16 TL divided by pi Z d to the 4. So as this shaft is in series, so theta is equal to theta 1 plus theta 2. So once we add it, we get 18 TL divided by pi Z into d to the 4. So D would be equal to 18 TL divided by pi theta G to the power 1 by 4. Okay. So we'll go to the next question. Figure shows the schematic for the measurement of velocity of air. The density is given through a constant area duct using a pitot tube and a water tube manometer. The differential head of water density is 1000 kg per meter cube. In the two columns of the manometer is 10 mm. Take acceleration due to gravity as 9.8 meter per second square. The velocity of air in meter per second is, so we need to find the velocity of air. So the answer is, the velocity of air is 12.8 meter per second. So let us see how we come. See, at this point, the pressure exerted by the water is mass of the water into G into this height H. Okay. So mgh is the pressure exerted by the water column. Now this water column pressure is being equal to the kinetic energy of the incoming air. So the air as it comes, so once it enters the pitot tube, it will try to push this water till the air velocity becomes 0. Okay, so the whole air velocity is compensated in making this manometer up. So mgh would be equal to the kinetic energy of the air, that is half of mass of air into velocity of air whole square, so half of mv square. So from here we see half of m air into free air was there. So half of rho air into volume of the air into velocity square is equal to rho of water into volume of water into GH. Okay. Now inside the manometer, the volume of air that is coming inside and the volume of water that is being displaced would be equal. So V air, capital V air is equal to capital V water. So volumes are constant. So from here we get the velocity of air is equal to 2gh into rho of water divided by rho of air. So which is equal to 12.78 meter per second, which is approximately equal to 12.8 meter per second. So we'll go to the next question. The values of enthalpy of steam at the inlet and outlet of a steam turbine in a Rankine cycle are 2800 kilojoule per kg and 1800 kilojoule per kg respectively. Neglecting pump work, the specific steam consumption in kg per kilowatt hour is, so we need to find it out. So the answer is 3.6 kg per kilowatt hour. So let us see how we get it. H1 is 2800 kilojoule per kg, H2 is 1800 kilojoule per kg. So work done per kg of steam would be H1 minus H2. So this is basically a enthalpy of steam entering the turbine, enthalpy of steam leaving the turbine. So that is the work done, which is equal to 1000 kilojoule per kg. Now as we are neglecting pump work, so our total work done is 1000 kilojoule per kg. Okay, if we had some pump work, then we had to minus that part. Okay, now specific steam consumption we actually can from the book we can directly get it as 3600 divided by 1000. That is the formula that we remember, but how it comes, if we need to understand, so that comes like this. Specific steam consumption would be the reciprocal of work done, so 1 by 1000, so it is kg per kilojoule. Now kilojoule is what? Kilojoule per second into second, that is kilowatt into second. So I can write 1 by 1000 kg per kilowatt, and then second we can write as hour. 3600 second is there in 1 hour, so it is hour divided by 3600. So what comes is the specific steam consumption is 3600 divided by this 1000 kg per kilowatt hour, which is equal to 3.6 kg per kilowatt hour. So we'll go to the next question. The integration 1 to 3 1 by x dx when evaluated by using Simpson's 1/3 rule on two equal subintervals each of length 1 equals. So this is a problem from numerical methods. Here we integrate it from 1 to 3 and our subintervals are of length 1. So from 1 to 2 and from 2 to 3 we have two intervals. So the answer is C, which is 1.111. Now how it comes? Simpson 1/3 rule says that integration x0 to x0 plus 2h fx dx is equal to h by 3 into y0 plus 4y1 plus y2. Y0 is what? Y0 is the value for x0. Here x0 is 1. Y1 is the value for the next, that is x0 plus h. Here that is 2, because our interval is 1, h is 1. Then y2 is the value of fx for x equal to x0 plus 2h, that is x equal to 3. Now we have put it in a table. For x equal to 1, fx would be 1. For x equal to 2, fx is half. For x equal to 3, fx is 1 by 3. Means fx is what? Fx is 1 by x, right? So 1 is 1, 2 is 1 by 2, that is 0.5, and 3 is 1 by 3. So integration 1 to 3 1 by x dx is equal to integration 1 to 1 plus 2 into 1. So I am writing it to make you understand more easily. Into 1 by x dx is equal to 1 by 3, h is 1, 1 by 3 into y0, that is 1, plus 4 into 0.5 plus 1 by 3. So it comes as 1 by 3 into, this part is was 1 plus 2, that is 3 plus 1 by 3, that is 10 by 3. So it comes as 10 by 9 in total, so 1.111. So we'll go to the next question. Two identical ball bearings P and Q are operated at loads 30 kilonewton and 45 kilonewton respectively. The ratio of the life of bearing P to the life of bearing Q is, so we need to find the ratio of the bearing life when they have two different operating loads and they are identical. Mind you, these are ball bearings. So the answer is, we know that the rated bearing life in million revolutions L is equal to C by P to the power small p, where C is the dynamic load capacity, capital P is the load applied, and small p is equal to 3 for ball bearing. So this you need to remember. Now this rated life L for P is equal to C by 30 to the power 3, LQ is equal to C by 45 to the power 3. Now the dynamic load capacity C is constant, C is same for both of the bearings as they are identical bearings. So from here we get this life of P, LP divided by LQ is equal to 45 divided by 30 to the power whole cube, that is 45 by 30 is 3 by 2 to the power whole cube, so this is equal to 27 by 8. So answer is 27 by 8. So we'll go to the next question. For the 4-bar linkage shown in the figure, the angular velocity of link AB is 1 radian per second. So this velocity, angular velocity of this link AB is 1 radian per second. The length of link CD is 1.5 times the length of link AB. So CD is 1.5 times of AB. In the configuration shown, the angular velocity of link CD in radian is, so we need to find the angular velocity of link CD in radian per second. So the answer is, see, the angular velocity omega AB we know as 1 radian per second. CD is 1.5 times of AB, that is given. Now AB is parallel to CD and both are perpendicular to AD. So AB is parallel to CD as both are 90 degree and both are perpendicular to AD. If we join AD, so both are perpendicular to AD. So in that case, the linear velocity VAB is linear velocity of AB is equal to linear velocity of CD. So VAB is equal to VCD at this instant. So from here, omega AB into AB, we know linear velocity is equal to angular velocity into the length of the object. So omega AB into AB is equal to omega CD into CD. So from here we get omega CD is equal to 2 by 3 radian per second. So the angular velocity of link CD in radian per second is, in radian per second is 2 by 3. So we'll go to the next question. A stone with mass of 0.1 kg is catapulted as shown in the figure. The total force Fx in Newton exerted by the rubber band as a function of distance x in meter is given by Fx is equal to 300 x square. If the stone is displaced by 0.1 meter from the unstressed position x equal to 0 of the rubber band, the energy stored in the rubber band is, so we need to find out the energy stored in the rubber band. So the answer is 0.1 joule. Now see how it comes. Energy stored in the rubber band is equal to integration of 0 to 0.1. That is, as our rubber band is displaced by 0.1 meter, so 0 to 0.1, then we have Fx dx. We know force into displacement is energy, so force into displacement is work done, and the energy would be equal, so Fx dx. So from here we get integration, energy stored in the rubber band would be integration 0 to 0.1 300 x square dx. So it is x cube by 3 comes, so it is 100 x cube of 100 x cube, and this lower bound is 0, upper bound is 0.1. So 100 into 0.1 whole cube minus 100 into 0 cube. So it is 0.1. So the energy stored in the rubber band would be equal to 0.1 joule. Okay. So we'll go to the next question. Consider the differential equation dy by dx is equal to 1 plus y square into x. The general solution with constant c is, so we need to find out the general solution. So the answer is, you see, if we see dy by dx is equal to 1 plus y square into x. So dy divided by 1 plus y square is equal to x dx. From here, if you integrate dy by 1 plus y square equal to integration x dx, let y equal to tan theta, then dy equal to differentiation of tan theta is equal to sec square theta. So sec square theta d theta. So this integration becomes integration of sec square theta d theta divided by 1 plus tan square theta. Now 1 plus tan square theta is what? Again sec square theta. So this cancels the only integration of d theta remains. The integration of d theta is equal to integration of x is what? X square by 2 plus a constant c. So theta is equal to x square by 2 plus c. So now theta is what? Theta is tan inverse y. So tan inverse y is equal to x square by 2 plus c. So y is equal to tan of x square by 2 plus c. So our answer is D. So we'll go to the next question. An unbiased coin is tossed 5 times. The outcome of each toss is either a head or a tail. The probability of getting at least one head is, so we need to get at least one head. Okay. Now let you see, H is the event of head and T is the event of tail. Now as only head or tail is possible and the coin is tossed 5 times, the total number of events is 2 to the power 5, which is equal to 32. Now the probability of getting at least one head is equal to, the total probability is 1 and is equal to the probability of 1 minus the probability of getting no heads. Okay, so at least one head, the probability we are asking, that means what? 1 is the total probability minus the probability of getting no heads. Now if we don't get any head, that means what? We have to get all tails. So all tails, there is only one event that has all tails, and so the probability that the event has no head would be 1 by 32. Therefore the probability that the events with at least one head would be 1 minus 1 by 32, which is equal to 31 by 32. So we'll go to the next question. A mass of 1 kg is attached to two identical springs, each with stiffness 20 kilonewton per meter as shown in the figure. Under frictionless condition, the natural frequency of the system in hertz is close to, so we need to find out the natural frequency of the system in hertz. Okay, mind you, it is in hertz and not in radian per second. So the answer is, the natural frequency is 32 hertz. So let us see how we are getting it. These springs are in parallel. So the equivalent spring stiffness K equivalent would be the addition of the stiffness of the individual springs, which is equal to K plus K, that is twice K, or 40 kilonewton per meter, as each spring is 20 kilonewton per meter. Now omega n is equal to root over K by n, that we know. So which is equal to root over 40,000 divided by 1. So omega n is equal to 200 radian per second. So omega n is 200 radian per second. We know Fn is equal to omega n by 2 pi. So which is equal to 200 by 2 pi, that is equal to 31.83, which is almost equal to 32 hertz. So the natural frequency of the system in hertz is 32. So we'll go to the next question. The shear strength of a sheet metal is 300 megapascal. The blanking force required to produce a blank of 100 millimeter diameter from a 1.5 millimeter thick sheet is close to. So basically we are given the shear strength, the blanking force, and blanking force, sorry, the blank diameter and the thickness of the sheet. Okay, so the answer is, it is option C, that is 141 Newton. Let us see how we get it. So shear strength tau is equal to 300 megapascal, that is 310^6 Pascal. Blank diameter D is equal to 100 millimeter, that is 0.1 meter. Thickness of the sheet T is equal to 1.5 millimeter, that is 0.0015 meter. Now blanking force F is equal to how much? The stress into area. Area is how much? As it is a circular cross section, so pi into D, and the thickness is T, so pi into D into T. So which is equal to the force into pi into D into T. So which comes at 141.372 kilonewton or 141 kilonewton. So we'll go to the next question. The ratios of the laminar hydrodynamic boundary layer thickness to thermal boundary layer thickness of flows of two fluids P and Q on a flat plate are 1/2 and 2 respectively. So this is what? The ratio of laminar hydrodynamic boundary layer thickness to thermal boundary layer thickness for the two fluids are half and 2. The Reynolds number based on the flat length for both the flows is 10^4. So Reynolds number is same for both the flows. The Prandtl number and the Russell number for P are 1/8 and 35 respectively. So for P it is given. So the Prandtl number and Russell number for Q are respectively. So we need to determine Prandtl and Russell number for Q. So let us solve it. So we have delta T by delta for P is how much? 1/1/2, which is 2. That is there. What we are given, that a laminar hydrodynamic boundary layer to thermal boundary layer for P is half. So thermal layer to hydrodynamic layer would be 1/2, which is equal to 2. Similarly for Q, it is 1/2. Now Reynolds number for both P and Q are same. Then we have Prandtl number for P is 1/8 and Russell number for P is 35. Now we know that delta T by delta is equal to 1.026 Prandtl number to the power minus 1/3. So del T by del of Q divided by del T by del of P is equal to Prandtl number of Q to the power minus 1/3 and divided by Prandtl number of P to the power minus 1/3. So we have, this is half divided by 2 is equal to Prandtl number of Q to the power minus 1/3 divided by 1/8 to the power minus 1/3. So this is how much? 1/4. Then this value is 2. So it becomes 1/2. So if we again Prandtl number to the power 1/3 would be then equal to, instead of 1/2 it will be 2. So Prandtl number of Q is 8. Okay. Next, we know the Nusselt number is equal to 0.332 into Prandtl number to the power 1/3 into Reynolds number to the power half. So Nusselt number Q divided by Nusselt number P is equal to Prandtl number Q to the power 1/3 into Reynolds number local Reynolds Rex to the of Q to the power half divided by Prandtl number P to the power 1/3 into Reynolds number of Rex Reynolds number of P to the power half. Now Reynolds numbers are constant. So we have Prandtl number of Q to the power 1/3 divided by Prandtl number of P to the power 1/3. So from here we get Nusselt number of Q is 140. So the Prandtl and Nusselt number for Q are respectively 8 and 140. So we'll go to the next question. The crank radius of a single cylinder IC engine is 60 millimeter and diameter of the cylinder is 80 millimeter. The swept volume of the cylinder in centimeter cube is So we are given crank radius, that is 60 millimeter. Diameter of the cylinder is given 80 millimeter. So we need to find out the swept volume. Now crank radius is 60 mm. So total stroke length would be twice of 60 mm, that is 120 mm. And then diameter is 80 mm. So we can find the area. So crank radius R is 60 mm. So swept length L is twice R. So 120 mm, that is 12 centimeter. Radius of the cylinder R is 40 mm, that is 4 centimeter. So swept volume would be, radius is there, so pi r square is the cross sectional area into length, would give us the swept volume, that is pi into 4 square into 12, so which is all equal to 603. So our answer is 603 centimeter cube. So we'll go to the next question. A pump handling a liquid raises its pressure from 1 bar to 30 bar. Take the density of the fluid as 990 kg per meter cube. The isentropic specific work done by the pump in kilojoule per kg is, okay, so we will check as the pump is raising the pressure from 1 bar to 30 bar and density is given. So we know specific volume of the liquid is 1 by rho, so it would be 1 by 990. The actual pump work per kg is given by what? W is equal to specific volume into pressure. So which is equal to 1 by 990 into 29 into 10 to the power 5. So the value is 2.93 kilojoule per kg. Okay. So we'll go to the next question. A spherical steel ball of 12 millimeter diameter is initially at 1000 Kelvin. It is slowly cooled in a surrounding of 300 Kelvin. The heat transfer coefficient between the steel ball and the surrounding is 5 per meter square Kelvin. The thermal conductivity of steel is 20 watt per meter Kelvin. The temperature difference between the center and the surface of the steel ball is, now we need to find out the Biot number and then we can understand what is the temperature distribution inside the steel ball. So the answer is, if we know the diameter, sphere temperature, current temperature we know H, which is equal to 5. Now Biot number is equal to H into LC divided by K. Now what is LC? LC is volume by area. So which is how much? Which is equal to 1 by 3 R for a sphere. So we get it as 0.002. So Biot number is 5 into 0.002 divided by 20, which is equal to 0.0005, that is 5 into 10 to the power minus 4. Now Biot number is much less than 1, it is almost equal to 0. So the resistance to conduction within the solid is much less than the resistance of convection across the fluid boundary layer. In other words, the heat moves faster through the solid than the heat moving from the solid to the fluid. Okay, so the temperature across the solid is much likely to be same as the heat is flowing much faster. So temperature across the solid is much likely to be same. Therefore, the temperature difference between the center and the surface of the steel ball is small. Okay, so once we know the Biot number, then we can very easily say what is the temperature distribution in this body. Okay, so with this we conclude the second part of the GATE 2011 mechanical engineering paper. I thank you all of you.